Good morning, everyone. Today we will cover a very interesting class of optimization problems where besides real optimization variables, some of the decision variables will be integer. And we will see how to formulate these kind of problems and in which practical applications they are useful. The outline for today's lecture is as follows. First, we will introduce the class of integer optimization problems. And afterwards, we will actually spend majority of this lecture with talking about applications of these optimization methods. And then, if time permits, we will also cover algorithms which are able to solve these optimization problems. And we plan to talk about two classes of algorithms. The first one is the so-called extensive enumeration. And the second one is a very clever heuristics which sometimes allows to solve these problems more effectively compared to the extensive enumeration approach. So let us take a look at what the integer optimization problems are, how they look like, and what are the properties. So integer optimization problems are optimization problems as any others, meaning we have objective function which we would like to minimize. So that's the function f here. We assume it's a scalar valued cost function. And it is a function of two classes of optimization variables. By x, we will denote the real valued optimization variables. And delta will be the integer optimization variables. So integers are denoted by this n here. So that's the set of the natural numbers. The index m here means that we have m of these integer variables. And this index n for the real decision variables means we are in the n-dimensional Euclidean space for the continuous variables. And we might have also constraints written in a very general form as inequalities. We know that equalities can be embedded into this framework here, or those equalities can also be made separate using some other function. Unlike the cost function, which is scalar valued, this constraint function g here can be vector valued, which means that we can have multiple of these inequality constraints. Okay? So that's the general setup of integer optimization problems. And as we already said, we have two classes of variables. We have the real variables. They are sometimes also called continuous variables. So they can take any value from the set which is formed by the constraints. But the delta variables, they are only integers, and they can only take integer values from 0 to infinity. Actually, we can very easily adjust the framework to also account for negative integers if we want. That's just a trivial change. But it is actually these deltas here which make these kind of optimization problems very difficult to solve. Essentially, the integer nature of those delta variables leads to non-convexity. And this is quite natural because we know what a convex... Well, actually, did we talk about convex set before? A convex set is a set where whichever 2 points we pick, the line connecting these 2 points always resides inside of the set. So this would be an example of a convex set. This set here is also convex because whichever 2 points we pick, the line segment connecting these 2 points is always contained in the set. However, a set like this would not be convex because we can find a counterexample to our argument. We can find 2 points which, when we connect them by a line segment, a part of the line segment is contained outside of the set. Okay, so these are non-convex sets. And now, if we just consider integer variables, then say that these are the integer variables that are consistent with the constraint. So this might be delta 1 and this might be delta 2. Okay, so this would be something like 1, 2, 3. Here it would be 1 and 2. Okay, so these are the integer values which satisfy the constraints, and we immediately see that the set of points creates a non-convex set, right? Because We just pick 2 points which are contained in the set, for instance, this point and this point. We connect them by a line segment, and the line segment is not contained in the set, right? Because the set is only formed by these isolated points. So the integer nature of the optimization variables introduces non-convexity. And we already know that whenever we hear that we have a problem which is non-convex, we are in trouble. Okay? Before, we have dealt with problems where the cost function was non-convex, and we have seen some algorithms to solve these kind of problems. One very recently was the sequential quadratic programming, but here it's actually even worse because we cannot even make some kind of continuous linearization or approximation of the non-convexity. So these problems are inherently non-convex, which means they are very difficult to solve. However, since we have only a finite set of values, so we always assume that we have also an upper bound on these integer variables. So they, in fact, they don't go to infinity, but there is an upper bound for each of these integer variables. That means we have only a finite number of them, which means that in the worst case, what we can do is we can try out all possibilities of these integer variables. That's basically what this extensive enumeration algorithm is about. So and then when we try each possible combination, essentially all those deltas, they go away because they just translate to a constant. So we end up with a continuous optimization problem, and we know how to solve that. Okay? So unlike the general I mean, these kind of problems are difficult to solve in general. However, if we assume some properties of the cost function and of the constraints, for instance, if the cost function and the constraints would be convex, then at least we have a guarantee that we can find the global optimum. Because we know that for general non-convex continuous problems, we don't even have such a guarantee. Like those randomized methods, they might converge to the global optimum, but sometimes they converge to a local optimum. Here, with the integer optimization problems, at least when we assume convexity of the cost function and of the constraints, I mean, even if we do make this assumption, the whole problem is still non-convex because of the deltas. But if these functions here are convex, then at least we have a guarantee that we find the global optimum. Because as we already said, we can, in the worst case, fix the values of deltas to all possible combinations. Then this problem just translates to a convex problem, so we are solving a series of convex problems for which we have a guarantee of finding the global optimum. So these kind of problems are difficult to solve in general, but they could be solved to global optimum. That's the message. However, this message is only valid if the cost function and the constraints are convex. If they are non-convex, we don't have any guarantee whatsoever. So those were the very general integer optimization problems, but very frequently in practice we restrict ourselves to the so-called binary optimization problems, where the only difference is the nature of those delta variables. Before, the deltas were integers from some range. Now in binary optimization problems, those deltas are only binary. So that means they can only take 0 or 1 values here. Okay? And actually, these kind of binary optimization problems, they can also solve the integer optimization problems because we can encode integers as binaries. Essentially, the encoding is by considering these deltas here as bits. Okay? And then we have at least 2 options how to encode an integer using bits. Right? One you are very familiar with, and that's the essentially the bitwise encoding of integers. Okay? So we take the base 2 of an integer, and we write the corresponding bit code of that one, right? So 6 here would be 110 in the binary system. So we know that it's 0 times 2 to the power of 0 plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 2, and that gives us 6. Okay? And actually, we can also derive the exact number of binary variables that are needed to represent integers of size at most delta star here. We know that we need log 2 of that upper bound, that many bits, but actually we have to make rounding to the sailing. Okay? So this operator here means the sailing operator, which means that if we get 2.2 bits that we need to represent a particular integer, we actually need 3 bits for that one. Okay? So that's one option, how to encode integer variables, meaning how to convert the integer optimization problem into a binary optimization problem. And this is actually the lowest possible number of additional binary variables that we need to introduce to model integers. There is one other way how to encode integers. Does anybody know how such an encoding is called? It's usually used in computer science and not strictly in optimization. Have you ever heard of the word unary encoding? Unary encoding, basically what it does is to each integer that we need to encode, for instance 0, 1, and 2, we know that if we would like to encode integers from 0 to 2 using the binary system, how many bits would we need? We would need 2 bits. Okay? But actually those 2 bits is a little bit too much, right? Because using 2 bits we can encode, in fact, 4 combinations. Okay? While we only need 2. So we are kind of wasting the potential here. Okay? The unary encoding, so this is the binary encoding. The unary encoding, on the other hand, what it does, it introduces a unique binary code for each integer that we need to encode. So in our case, we are going to encode 3 binaries, and actually the unary code is always such that it contains only 1 non-zero entry in the code, and exactly 1 non-zero entry in the unary code. Okay, so the integer 0 could be encoded using 3 binary variables, like this. The integer 1 would be 0, 1, 0, and the integer 2 would be 1, 0, 0. Okay? While before we only had 2 binary variables. Okay? So someone can argue, like, why should we even use the unary code which requires more binary variables? Here we only had 2 binary variables, and here we had 3. And actually the complexity of these optimization problems depends mainly on the number of binary variables. The higher the number of binary variables, usually the more difficult it is to solve these kind of optimization problems. So why do we even propose this unary encoding as a possible way of encoding integers if it introduces more binary variables, 3 versus 2? It actually all boils down to how many combinations are feasible in this encoding and how many combinations are feasible in this encoding. Here with the binary encoding, we actually have 4 combinations which these 2 binaries can produce. Meaning the solver, the algorithm which will be solving this kind of problem, has to investigate in the worst case 4 combinations. Okay? While in this case, by adding the very strong condition which says that the sum of the deltas is equal to 1, the solver only needs to explore 3 combinations. Okay? And this is a very trivial case where the number of binary variables are low. But in practice, when we are encoding integers, say, to 10 or 20, then this one can lead to significant advantage over the binary encoding. So the message here is that people usually say the more binary variables we have, the more difficult it is to solve the problem. This is only half of the story. What they don't say or what they don't realize is that it is not about the number of binary variables, it's about the number of feasible combinations of these binary variables. So here, even though we have more binary variables, we have smaller number of feasible combinations. Here we have smaller number of binaries, but actually a larger number of feasible combinations. Now, this one can also be kind of ruled out rather easily. Can anybody tell me a condition which rules out that these binaries will be set to these two values? Tell me a condition which is infeasible if delta 1 is 1 and delta 2 is also 1. And that condition must be feasible for any other combination of binary variables. But that would be, so if we would assume that this is the condition that we are looking for, meaning delta 1 plus delta 2 is equal to 1, then it would also rule out this combination which we need to keep. So this is not the condition that we are looking for. Inequality in which sense?
Which says that the sum has to be smaller or
equal to 1, right? So if to this binary encoding we would also add this condition, then the solver, it might try this combination, but it will very quickly see that that combination is infeasible, because it will check this constraint, it will see that the constraint is not satisfied, so it will not attempt to solve the problem for this binary combination. So the bottom line here is that we can make the binary code almost as efficient as this one. The only trouble is that now, why stop at 2? Why not stop at 3? Okay, so here, okay, 3 actually is fine. Let's say 4. 4 is the kind of the number of the upper level of the integer that we need to encode. Well, first of all, how many bits do we need in the binary encoding now? Yes, we need 3 bits, right? So delta 3, delta 2, delta 1. So this code would be 0, 0, 0. This would be 0, 0, 1, 0, 1, 0, 0, 1, 1. And now we have 1, 0, 0, right? Now, can you tell me a condition which says essentially that the remaining combinations that we can encode using 3 bits? I mean, we can also encode the integer 5, right? We can also encode 6, and we can also encode 7. And now what we want to say is, what are the conditions which make these cases here infeasible, such that they quickly tell the solver not even to bother with this one? Well, first of all, the situation is extremely easy here, right? So we need as many binaries as we have the upper level of the integers that we need to encode. So here we would also need delta 4. And for the integer 4, the unary code would be like this. Okay? And the condition is still just a single condition which says the sum of deltas is equal to 1. So even though we have added a new integer, we didn't have to introduce a new condition. It is the same condition as before. But now we actually need to do quite a lot of work to kind of reject these kind of combinations. Okay? And it makes actually a nice exercise to come up with the conditions which are feasible here but are infeasible here. So probably it would be something like delta 3 plus delta 1. What? Is lower than 1. I do agree with that. So, and we need to always check whether all these cases are feasible for this condition. Okay, so here it's feasible because 0 is smaller than 1. Here it's feasible because 1 is smaller than 1. This one is feasible. This one is feasible. And this one is 1 plus 0 is also feasible. But this one is infeasible, right? So this condition rejects this here. But this condition is feasible for this row here. So we need more conditions and so on. So, and actually it is far from trivial to come up with those conditions which only leave the perfect code inside of the optimization problem. So that's the message. With the unary encoding, we always have a guarantee that the solver only explore those combinations which are really feasible, and it never looks at combinations which are which are like kind of generated by the code but are not to be considered in the optimization problem. However, with the binary encoding, we might have smaller number of binary variables, but actually if we are not careful, if we do not add these conditions, then the solver actually does more work than here. So the main message here is, yes, it is kind of, the complexity of this optimization problem depends on the number of binary variables, but that's not the whole story. The precise answer would be the complexity depends mainly on the number of feasible combinations of these binary variables here. Okay? So that's about the conversion from the integer formulation to the binary formulation. So every integer optimization problem we can convert to a binary optimization problem, either by using binary encoding or unary encoding, and we prefer the unary encoding for that. So that's why from now on we will only focus on binary optimization problems, because they kind of internally can also represent integer optimization problems. So if we have an algorithm which solves a binary problem, we can also solve integer problems using the same algorithms just by providing this kind of encoding here. Okay? So that's one point. And when talking about complexity, meaning how much time does it take to solve an optimization problem, besides the number of binary variables and the number of feasible combinations of these binary variables, what the other aspect which makes some of the problems rather easy to solve and some rather difficult to solve is what is the type of the cost function and of these constraints here. And actually we might have both of these functions, meaning the cost function as well as the constraints as non-convex functions. And then the nomenclature is that we call such a problem as mixed integer nonlinear program, and the shortcut that you will often see is MI-NLP. MI means mixed integer, NLP means nonlinear program. Okay? And by the way, it's mixed integer. That mixed means that we have both continuous as well as integer variables. That's what mixed means here. These problems are the most general ones, but also the most difficult ones to solve. And we know why. Because even if we don't consider integer variables, just solving nonlinear programs is difficult because they might have multiple optima and so on. We know that we get a simpler problem if we assume that the cost function is convex. It's actually not just convex, but it's also quadratic. And these constraints here are linear functions of x and delta. These kind of problems we call the mixed integer quadratic programming problems. And if we furthermore assume that the cost function is linear, then we end up with mixed integer linear programs which are abbreviated by MILP. And actually, the complexity of these problems grows from the bottom to the up. Okay, so we know that linear programming problems are pretty much the easiest constrained optimization problems that we are aware of. Quadratic optimization problems are a little bit more difficult because we need to do matrix inversion, while there was no matrix inversion in the linear case. And the nonlinear programs are the most difficult because we can use sequential programming, which means we are solving a bunch of these problems to solve one instance of the mixed integer nonlinear program. So therefore, when formulating your optimization problem, you always try to formulate it as mixed integer linear program. If that is not possible, then at least formulate it as a mixed integer quadratic program. If even that is not possible, you are in big trouble, because these kind of problems, to solve them even to local optimum, is very challenging. Okay? While these problems, at least for a low number of binary variables, they are, well, rather easy to solve, as we will see in the algorithmic session of the class. Okay, so that would be for the mixed integer optimization problems. Sometimes we have a problem where we only have integer decision variables, meaning we have no continuous optimization variables. Those x's don't appear in the problem, and we will see some instances of these kind of problems. Then the nomenclature says we just drop the mixed part of the name of the problem. Okay, so we have integer linear programs as the most easy ones. A little bit more difficult are integer quadratic programs, and the most difficult ones are integer nonlinear programs. And if we assume that those delta variables are only binary, then the nomenclature says we are talking about either binary linear program, binary quadratic program, or binary nonlinear program. As before, the complexity grows from the bottom to the up, as expected. Okay? So far for the kind of the nomenclature, how these problems are set up. And essentially the reason why I'm showing these kind of formulations is that the solvers, which ultimately solve these problems, they expect the input in roughly this form. So they require us to provide the cost function, the constraints, the nature of the optimization variables, whether they are continuous or whether they are integer or binary, and they run some math inside, and hopefully they provide us with the optimal solution. So that's why it is important to know like in which form these kind of problems are set up. And then once we know that, let's take a look at some interesting applications of integer optimization. And there are actually many very interesting practical problems that can be set up and solved as integer optimization problems. Actually, the classes of problems is much wider than those which I will be mentioning here. And some of those additional ones we will also cover in the exercises. So let's start with one of the very standard problems that fits perfectly into the category of integer optimization problems. And it's a so-called 0-1 knapsack problem. So essentially you are a burglar and you want to steal as much goods as possible. You know that your backpack has limited capacity in terms of weight that you can carry. And the objective here is to choose which of these products you will take such that you, of course, take the maximum value. That's the knapsack problem. And the 0-1 nature says that from each product we have exactly one piece available. And we only optimize whether we want to take a particular product into the backpack or not. Okay? So the optimization variables here, these x's are binary variables. Okay? And the task of the optimization is to decide which items to take such that we maximize their value, the value of our backpack, and we respect the weight constraint here. So can somebody tell me how such an optimization problem would be set up? Clearly, we have a cost function that we want to maximize. We know that maximization, we can easily convert that to minimization just by minimizing the minus value of the cost function. And we have constraints. So what would be the optimization problem here? Maximize what? Okay, let's call by, let's do it here, sorry. Well, we have to introduce some symbols clearly. So let's call VI, that would be the value of the ice item here. W would be the weight of the value of the item, sorry. Capital W would be, in our case, those 15 kilograms as the constraint on the backpack. And we have xi as optimization variables which are only binary. Okay? So now how does the optimization problem look like? So we are maximizing something. What are we maximizing? So you would like to maximize the value. Okay? So if we take the ice, well, that's the value of the ice item. But what tells us whether we actually take the item or not? That's xi, okay? So we have to multiply it by xi, and then we have to sum it over the number of products that we have available. Okay? So that's the cost function that we would like to maximize, and what is the constraint? It's actually two constraints that we need to write there. First is the weight. So how do we express the total weight of the items inside of our knapsack? That's the weight of the ice item times whether we take the item or not. We sum it up over all items, and that has to clearly be less than doubling, right? Do we need to write that this weight should only be non-negative?
No.
Why not?
Because the second constraint will be if we take or if we do not.
Yeah, so the second constraint is essentially takes care of that. So the second constraint, which is very important, and this is actually what makes the problem difficult, is that we say that xi can only be inside of this finite set. Okay? Technically speaking, it is a constraint in the optimization problem, as we will see in a second. Okay? So that's the overall optimization problem that we need to set up. Okay? Now, can anybody try to find the optimal solution here? Just by looking on that problem, and maybe also explain, like, how did you come to that solution? It's not easy, right? At least it's not obvious. Sure. That's kind of the heuristical approach, which does not always give the best solution. Here, incidentally, yes, it works. But what if the largest value would be here and would be, for instance, 5? Okay? Then we would put one item which weighs 12 kilograms, has a value of 5, and then we only have 3 kilograms to actually use, right?
So the better approach is to calculate the ratio between price and weight?
Maybe. Maybe. Okay, let me ask a different question. What if we get rid of this constraint and instead we assume that xi is not binary, but it's a real value from 0 to 1? What we have just done is we have relaxed the problem. A relaxation means take a problem, which only allows two values, and pretend for a second that we allow all values from inside of this interval here. This is the relaxed problem. What kind of problem is this? Is it an easy problem or a difficult problem? The previous one was difficult, right? This one is an easy problem. What kind of a problem is that? That's linear programming, and we know we can solve that very easily, very quickly. That's like 1 millisecond on a computer, even faster for a problem of this size here. Okay? So let's solve this problem here, and you could do it on a piece of paper using the simplex method, and then you would find this solution here. And what we see here is something rather interesting. Some of these optimization variables in the optimum have a binary value, 0 or 1. However, we have one which is somewhere in between. And actually, this makes the best use of the knapsack capacity that we have available. This would lead to the highest value of those products that we can take with us. The only problem is that we don't want to solve a relaxed problem, we want to solve the binary problem. So actually somebody might now say, okay, but 0.58, let's just round it. Okay, and just rounding it would mean let's put 1 here, but then we can easily see that the capacity of the backpack would be violated here, because we would be adding a large item there. So the bottom line here is that sometimes these kind of relaxed problems can give an integer solution or a binary solution, but usually not always, and usually they don't. And just rounding those non-integer values does not give the expected solution. However, we will see that still these kind of relaxation problems they are useful when coming with a good heuristics how to solve the original problem. So we will essentially revisit the idea of relaxation, and we will see how it allows us to solve the problem faster compared to just trying out all possibilities. By the way, there is one naive way how to solve this optimization problem. Since we know that all variables are only 0, 1, let's try all possible combinations. Evaluate the cost for each possible combination and just pick the combination which gives the best cost. Okay? That's essentially what the extensive enumeration approach is about. So here in this example, if we return to the original problem where the decision variables are binary, then actually this is the optimal solution. So we take these 4 items here and we leave out the green one. That's the optimal solution which has the best value of the objective function. And you will practice with these kind of problems. You will not solve the problems by hand. You will use a software. And what you will practice mainly is how to formulate these problems and how to interpret the results. Okay? So that's the illustration here. And by the way, these kind of knapsack problems, I mean, they look quite funny. I mean, we are talking about burglars and so on. But I mean, imagine that you are making purchase for your company, okay? And you have multiple suppliers from which you can choose. And this is the price that you are taking with you. And this might be some kind of qualitative criterion that you would like to optimize. Okay, so it doesn't always have to be the weight and the price. It can be like the quality and density of the product, whatever. We don't need to maximize the value. We might, for instance, minimize the volume of the items that we would like to put in, subject to the cost constraint. Okay, so these kind of problems, they are very general. And many practical applications, they fit into this framework. Okay, so we are talking about problem frameworks. So this knapsack problem is very general, and many interesting problems fit into this category here. And this is the 0, 1 knapsack problem, means we have, from each item, we have exactly 1 piece, and we either take the piece or we don't. Slight generalization of the knapsack problem is called the bounded knapsack problem. Essentially what it says is that from each item we have Ci kind of pieces of that item available for us. Okay? And we would like again to maximize the value that we fit into our backpack, subject to keeping the overall weight constraint at this level. So notice now that these optimization variables are integers which go from 0 to Ci. The Ci can be different for each item, or it can be the same thing. Now, what would be the equivalent of unary encoding for this situation here? How can we solve the problem where, say, from each item I have 5 pieces available? How can we equivalently encode this problem as a binary optimization problem? What would change in this picture if we would like to solve the problem using only binary variables? So we still want to have the ability to pick, say, up to 5 pieces of each item.
Unary codes, for example.
Yeah, but what would it mean here in this picture? Like I'm trying to come up with kind of naive explanation of what really binary and unary encoding is. Essentially, we would just make copies of these items here. Okay, so the green box, we would add 4 more copies of that, and each of that we can only take 1 time. So essentially we are doing a binary encoding of the integers that we have here. Okay. So that would be the equivalent of the binary encoding for this particular scenario. So again, it just means that even though we have an integer optimization problem here, this problem can be converted into binary optimization problem, using, for instance, the binary encoding. Okay. What would be the equivalent of unary encoding? Okay? So I'm just going to write like those green boxes. Okay? So let's suppose we can take 5 of them. Okay? What would be the equivalent of unary encoding?
There are 5 codes.
5 codes. And each of them encoding, how many pieces do we take? Okay, so the first code would be like this. 1, 0, 0, 0, 0. Because we know we have 5. The second code, which is 1, 0, 0, 0, 0, encodes that we want to take 2 of these boxes. Meaning the situation is like this. The third code says we are taking 3 boxes. And so on. Okay? So having just these 5 boxes separate, that would mean the binary encoding, and having these piles would mean that's the unary encoding in our binary optimization problem. Good. So let's return back to this problem now that we know that we can actually solve it as a binary optimization problem. And let's attempt to solve the problem. Let's say that the boundary here is Ci. Well, actually, we can do the same thing as before. We can do relaxation. Then let's solve the relaxation using 5 copies of each item. And this is the optimal solution. Actually, 3.75 times 4 is exactly 15. So we are maximizing the weight. And we are also maximizing the value. However, we see that this result here is not integer feasible because this value here is not integer. So actually, the optimal solution for the integer optimization problem is 3 pieces of this item and 3 pieces of this item here. Okay. By the way, is this a mixed integer problem or just an integer problem? Do we have continuous optimization variables? We don't. We only have integer optimization variables or binaries in the 0, 1 case. So this is just the binary or the integer optimization problem. It's an integer linear program in particular. That's the easiest from those integer problems that we are aware of. Okay? So that's the knapsack problem. Actually, integer optimization problems can be also used to solve an example that we have already discussed in the very first lecture. We have 4 swimmers that have to swim on 4 intervals of the medley competition, and we have to devise the optimal composition of the medley, assuming that those swimmers will really swim at the level of their personal record here. Okay? And the optimum actually is given by this composition. The question is, how can we find this composition? By solving an optimization problem. That's the question now. So we have to again formulate the optimization problem. For that, we first have to set up the symbols that we are going to use, and then we have to see how those symbols play together to actually represent the optimization criterion plus the constraints. So what about ideas? So let's say that we will call by Tij, that would be the time which the i's swimmer requires to swim the j's style. Okay, so the first index is for the row, the second index is for the swimming style. Okay, and these are just constants. Now, what would be the optimization variables? Any suggestions? By the way, look here. Essentially, what we are looking for is the optimal placement of these circles such that the sum of the numbers in those circles is minimized. That's how we find the optimal composition. Okay? And in each cell, we either do have a circle or we don't. Okay? So let us denote by xij the fact whether a circle is contained in the ith row and jth column or not. Since we only have binary decision, it means that these variables here are only binary variables. Okay? So this would be our binary variables. Now, how can we now denote the total time which the whole medley takes to complete the competition? What would be the swimming time, the overall swimming time, in mathematical terms? And we know that we want to minimize that overall time. So there is no circle here, so the corresponding x is 0. Okay? So it would be like 0 times this number, plus 0 times this number, plus 1 times this, plus 0 times this, plus 0 times that, 0 times that, and so on. Okay? So we can actually write it as taking the sum over each row. Inside of each row, we are taking the sum of each column, and we are multiplying the constant times the optimization variable. Okay? And we would like to minimize this overall time. Okay? So that would be the cost function. What is the type of the cost function with respect to the optimization variables? Is it a linear function? Is it a quadratic function? Is it a non-linear function? I mean, forget about the sums. Sums are linear operations. So a function just t times x, where t is a constant and x is an optimization variable, is a linear function. Okay? So this cost function here is linear. Okay? But we also know that we have some constraints. First, write the obvious constraint, which says each optimization variable is a binary variable like this. Okay? But now look at the picture again. It says something important about the choice of these decision variables. By the way, those decision variables we can interpret as a matrix. This would be x11, x12, x13, x14, x21, all the way to x44. Look at how many circles do we have in each row and in each column. And try to think why it is so. Why cannot we have 2 circles in the same row? What would it mean physically? We could have a situation like that. You will practice that in the exercises. And actually, it can provide us with even faster swimming team. If we assume there could be 2 circles in one row, what would it mean practically? If you can interpret that consequence. Right, so, well, that's because the rules forbid that. So essentially, we are now encoding the rules of the competition into the optimization problem. So can you tell me what are the rules of the competition here? Yeah?
The sums, rows, columns.
So the row sum, what? The row sum has to be equal to 1 for each row. If it has to be the row sum, then we must sum over j's, because j's are for the columns. And this is for each row. So that's for each row. So each swimmer can swim, must swim at exactly one of these pieces. And the second one is the column sum, which also has to be equal to 1 for each column, and says what? What exactly does it say?
That 2 swimmers cannot swim the same style.
Right, yeah. Which, by the way, would imply that one of those styles would be uncovered at all.